Welcome back to One Dimensional Kinematics, The Adventures of Jim and Cindy, and we are finally going to be looking at gravity and freefall.
Alright, finally doing some problems involving gravity. A ball is thrown straight up. At what point is it moving the fastest? At what point is it moving the slowest? So this might be a little bit hard. You might just want to kind of throw a ball around, just kind of see. But what most people think of is either the beginning when it's thrown initially, or at the end when it's coming back down. They're usually thinking that at this point or this point it's going the fastest. And the truth is, without air resistance, which we don't do in the beginning of physics, is at this point and right here, it's going to be going the same speed. So if you threw it at 10 miles an hour, it'd be going 10 miles an hour up over here, but 10 miles an hour down over here. Okay, so the beginning of where it's thrown is going to be the fastest. Interesting fact is, wherever it's parallel to each other, let's say for example it's 7 miles an hour here, it'll also be 7 miles an hour this way, just going in different directions. Okay? But where it would be the slowest is going to be on top right here. And at the very top, the velocity is actually going to be 0 miles an hour or 0 meters per second. So at what point is it moving the fastest? At what point is it moving the fastest? It's going to be where it's thrown and when it comes back. At what point is it moving the slowest? It's going to be at the very top. Okay, let's look at the next example. Conceptual question number 10. A ball is thrown straight up. Does it take more time to go up or come down? Or is it the same amount of time? So we're wondering, sorry, that's bad, for it to go all the way up and then all the way back down, which takes more time? And this another physics concept is however long it takes to come up, it's going to take the same amount of time to come back down. Again, with no air resistance, which we're not going to be using. So for example, if it takes 5 seconds to go up, it's going to take another 5 seconds to go down. Okay, so it's going to take the same amount. So it's going to be the same. Alright, now let's look at some math problems. Harry and Cindy, back at this. Harry and Cindy decide to go to New York together. What happened to Jim? They decide to visit the Empire State Building and climb to the top, 380 meters. When they get to the top, Cindy decides to drop a penny to make a wish. How long does the penny take to reach the ground? Alright, so let's draw this out. Dropping a penny, going down. Alright, so let's just kind of draw it out. So we know the Empire State Building is 380 meters. So let's write down some things. So we know whenever we're doing free fall problem, let's start with the acceleration. We know that the acceleration, whenever we do a free fall problem, whenever an object isn't touching anything or anything like that, it's going to be moving with an acceleration negative 9.8 meters per second squared. And we also know that this penny is going to be dropping down 380 meters. So I'm going to say the displacement in the y direction is going to be falling down 380 meters. And I put a negative because it's going downwards. Next thing is, what we're looking for is the time. But we only have 2 pieces of information. Remember, we need 3 to solve anything. So now a key thing that we're going to see here is when they get to the top, Cindy decides to drop a penny. This is a key word, drop. What this means is when something is dropped like that, that means the initial velocity of the penny is going to be 0 meters per second. If she were to throw it down or throw it up, it would have an initial velocity, but since she only drops it, that means its initial velocity is 0. Now what we're going to do, we're going to look at what formula has all 4 of these, and we're going to see it's going to be this one over here. I just put the y's there because it's just showing us in the y direction. So displacement in the y equals v initial y t plus 1/2 a y t squared. So negative 380 is equal to 0 plus 1/2 negative 9.8 t squared. And what we get is the penny is going to be taking 8.81 seconds to hit the ground. Next question, how fast is the penny going when it reaches the ground? So we want to know when it reaches the ground right here, what is the velocity? Same thing, we're going to find what we know. Acceleration to y, negative 9.8 meters per second squared. Displacement in the y, negative 380 meters. Initial velocity in the y, 0. But now we also have the time, which is 8.81 seconds. So we're going to look at our formula sheet, and we actually have some choices now. Oops, sorry. And we're looking for what the velocity final is. We have some choices. We could either use this one here, or we could use this one here. And this one's simpler, so I'm just going to use that one. So acceleration is equal to v final y minus v initial y over t. So acceleration, as we know, negative 9.8. Velocity final, that's what we are looking for. Initial velocity is 0, and the time 8.81 seconds. And what we get is the final velocity right before it hits the ground is 86.3 meters per second. So a lot of times people think, oh, when it hits the ground, it's not going to be moving. But no, when it's about to hit the ground, it's moving very, very fast. So just know when it's about to hit the ground, that doesn't mean it's going to be 0. When it's going to be hitting the ground, it's going to be going very, very fast. Okay. Example number 27. Sorry. Let's come back here. So when she drops the penny, what did she wish for? Cindy wishes that Harry would take her to the winter dance. What about Jim? Alright, let's see. Let's see what Harry wishes for. Harry's on top of the Empire State Building, 380 meters, and decides to throw his penny down with the velocity of 5 meters per second. He makes a wish too. Let's see what he wishes for. What is the velocity of the penny 2 seconds later? Alright, so we're going to do the same thing. We're going to draw this out. 380 meters. And he throws this penny down. So, same thing, you want to write down everything you know. Whenever gravity is the only thing touching it, that means it's going to be accelerating, negative 9.8 meters per second squared. Let's see. So what we're looking for is what is the velocity of the penny 2 seconds later. So we're looking for at 2 seconds. So 2 seconds. We can't do the displacement as 380. The reason we can't do that is because this penny, we don't know how far it is after 2 seconds. It's probably not going to be 380 meters though. So when we have but we do have the initial velocity. He's going to be throwing this down at 5 meters per second. But what's important to know is he's throwing it downwards, so that means it's going to be negative. Okay? And we're looking for what is the velocity of the penny after 2 seconds. So we're looking for velocity final. So now, let's do some math. Acceleration equals v final minus v initial over t. Negative 9.8 equals v final, which we're looking for. V initial, which is negative 5 over t, which is 2 seconds. And what we're going to get is v final is equal to negative 24.6 meters per second. Next question is, how much has it fallen in those 2 seconds? So we're looking for, so it's going to be falling a certain distance, and we want to find what that distance is in 2 seconds. So acceleration in the y, negative 9.8 meters per second squared, time 2 seconds, initial velocity, negative 5 meters per second, and we actually also have the final velocity now, negative 24.6 meters per second. So Well, and also how much has it fallen, so we're looking for what the displacement is. We're going to look at our formula sheet, and we have a few options, but I'm going to just use this one over here. And what we can do is the displacement of y equals v initial y t plus 1/2 ay t squared. And we get displacement of y is equal to -5 2 seconds plus 1/2 -9.82 squared. And then we're going to get an answer of -29.6 meters. And it says how much has it fallen, so that's just asking for the distance. So I'm just going to change this into 29.6 meters. That's how much it fell. Okay. Ooh, and what did Harry wish for? Harry wishes for the new Air Jordans. They don't really seem to be on the same page over here. Or let's look at a conceptual question. You drop a penny. After it travels 4 meters, you drop another penny. As the pennies fall, does their distance away from each other increase, decrease, or stay the same? So let's just think about this. You drop a penny. Okay, so this penny is going to be falling down, and then when it reaches a certain distance, let's say it reaches that much, then you drop another penny. And the question is, as this one falls down and as this orange one falls, what's going to be happening to the distance from each other? Is the distance going to decrease, meaning this orange one, this orange one is going to start catching up? Is it going to stay the same, meaning it's just going to stay the same the whole time? Or is it going to increase, where this blue one is going to be getting further and further away? So this is a little bit hard to think about. One thing that we know is that both of these, when it's dropped, is going to be experiencing an acceleration of -9.8 meters per second squared. And you might be thinking, since they both have the same acceleration, that must mean that they must stay the same, the amount of distance. However, what we know is for this blue one, it had a bit of a head start, so they're both getting faster and faster, but this blue one is always going to be faster than this orange one. So since this blue one is always going to be faster than this orange one, what that means is it's going to be getting further and further away. Again, this blue one is always going to be faster than this orange one, because when this orange one gets dropped, it's going 0 meters per second. And if it was dropped after 1 second, that means this is going 9.8 meters per second. And when the orange one is getting faster and faster, and let's say it goes 9.8 meters per second, by the time it's going 9.8 meters per second, this blue one now is going to be going 19.6 meters per second. So it's just going to be getting faster and faster no matter how fast the orange one tries to catch up. So the blue one's going to be getting further and further away from each other. Okay, it's a little bit hard to think about, but just know, since this one dropped first, it's always going to be traveling faster than the orange one. Okay. Example number 28. Jim realizes that he screwed up at the last engineering competition. Back at the competition. So he decides to build a rocket to impress Cindy. The rocket is fired into the air and reaches its highest point 4 seconds later. With what velocity was the rocket fired? Alright, so let's draw this out. Okay, trying to impress Cindy again. I don't know. Usually doesn't really work out for you, Jim, but let's see. So he has this rocket. He has it take off. It goes like this. The rocket is fired into the air and reaches its highest point 4 seconds later. So, how long it takes to get to the highest point is 4 seconds. And what we're looking for is with what velocity was the rocket fired. So when this rocket starts to shoot up, what was its velocity? All right, let's write down everything we know. We know that, we know always, remember, when gravity is the only thing touching it, the acceleration is negative 9.8 meters per second squared. We know it's going to reach its highest point at 4 seconds. What we're looking for is the initial velocity that the rocket takes off with, but we only have 2 pieces of information. The next piece we should know is also at the highest point, at the end of that 4 seconds, the rocket is going to be slowing down, and momentarily come to a stop, so that the final velocity after these 4 seconds is 0 meters per second. Now that we have 4 pieces of information, we're going to look at our formula sheet, and we're going to notice this equation has all 4 of these variables. So we're going to use that formula. Acceleration is equal to v final minus v initial over t. And we get negative 9.8 is equal to 0 minus v initial, which we're looking for, divided by 4. And we find that the initial velocity of the rocket is 39.2 meters per second. Part B now asks, how high did the rocket go up? So we're looking for this highest point right here. So what we're looking for is what that displacement is in the y direction. Again, the piece of information that we know initial velocity is 39.2 meters per second. Final velocity is 0. Time is equal to 4 seconds. And acceleration is negative 9.8 meters per second squared. So let's try to figure this out. Let's look at our formula sheet. We have 4 pieces of information and then what we're looking for. So we have some options. We could use this one here, or we could use this one here. I'm going to use this one here. So we have displacement in the y equals v initial y t plus 1/2 ay t squared. Displacement in y is what we are looking for. V initial in the y is 39.2. The time to get to the highest point is 4 seconds, plus 1/2 negative 9.8 4 squared. Then we get what the displacement is, and that is going to be equal to 78.4 meters. So, Jim is ecstatic about the results and can't wait to tell Cindy. Well, we'll see if Cindy's happy about this. Alright, interactive example. Have one volunteer try to catch a dollar bill in the air, just like in the picture. So you can try this with your friends or anything. If a dollar bill, which is dropped, which is 0.155 meters long, so let's say this is 0.155 meters long, what is the minimum reaction time needed to catch the dollar bill? Okay, so let's just write down everything we know. When this dollar bill is dropped, it's going to have an initial velocity of 0. What's going to be pulling it down is gravity, which is negative 9.8 meters per second squared. The dollar bill is going to be falling down a distance of negative 0.155 meters, while this person needs to catch it before it falls down all the way. So we're looking for time. Now, we're going to look at what formula has all 4 of these, and we see this one does, and we can plug it into that formula. Zero plus 1/2 negative 9.8 t squared. Do a little bit of math, and we get you need to have a reaction time of 0.178 seconds, which is pretty difficult. So probably people will have a very hard time being able to do that.